This is Not Your Dad's Math. I'm Mike, and today we are engineering an LED test circuit. In this first part, we'll be designing the circuit in KiCad. We'll start by creating a new project called LED Test. We'll design our circuit in the schematic editor, so click into it. We want to test an LED, so let's add a symbol for it. We'll choose the symbol for a generic LED. Our goal is to run between 0 and 20 milliamps of current through the LED to light it up. We'll achieve this by adding a resistor in series with the LED. Let's connect a wire between these components. Now, imagine that we can control the voltage at this point in the circuit and force it to be exactly 1 volt. Then, using Ohm's law, we can set a current of 20 milliamps through the resistor. 1 volt divided by 20 milliamps gives us 50 ohms, so we'll pick a standard resistor value of 47 ohms. And of course, we have to connect this resistor to ground for this to make any sense. Next, we need to design a way to hold this point in the circuit at 1 volt. If we only use passive components, this can get complicated. So let's do this the easy way and use an op-amp. For this circuit, we'll use the LM358. It can be powered by a single supply, and its inputs and output can be driven to ground. The LM358 has 2 channels. We'll use the first channel to drive the LED. We'll move the second channel out of the way and save it for later. And we'll park the power supply pins somewhere up here. The next idea is to drive the non-inverting input with 1 volt. When we connect it in a feedback loop, the op-amp will hold the inverting input at the same voltage. This is how we're able to set the voltage at this point in the circuit to 1 volt. Virtually no current will flow into the op-amp input. Whatever current flows through the resistor must also flow through the LED. This means that we've created a fixed 20 milliamp current source to drive the LED. Next, we'll provide a way to dial down the input voltage from 1 volt all the way down to 0. We'll achieve this by connecting a potentiometer to the op-amp input. The size of this potentiometer won't matter, but we do want to use a linear pot to scale the input voltage evenly. We'll connect one side of the pot to ground and the other to a 1 volt reference that we'll provide from the second op-amp channel. We'll create a 1 volt reference using a voltage divider. Now all we have to do is buffer the output and connect it to the second side of the pot. We'll connect our resistor divider to ground and a 9 volt supply. It's easy to divide this voltage. We need to drop 1 volt across the bottom resistor and 8 volts across the top. We'll get close enough by choosing a resistance of 1K for the bottom resistor and 7.5K for the top. To recap, we'll divide the power supply to create a buffered 1 volt reference in the first stage. We'll use a potentiometer to dial between 0 and 1 volts to drive the second stage. Then using the second stage's feedback loop, we can drive a current between 0 and 20 milliamps through the LED. Now we can connect our op-amp's power pins. We'll add a large electrolytic capacitor across the power rails. I'll use 100 microfarads, but 10 or even 1 should work too. For op-amp stability and as a good design habit, we'll add a small capacitor across the op-amp's power pins. A 10 nanofarad ceramic capacitor will do the job. Let's get everything connected and tidy things up a bit. Now we're ready to run the electrical rules checker. Click Run ERC and see if we get any errors. We see two messages about input power pins not being driven. We need to use the special power flag component to tell KiCad where our power comes from. Simply connect these to the 9-volt and ground nets, and we'll be good to go. Now we can run the electrical rules checker whenever we make changes. Let's make a change. We're asking this op amp to drive up to 20 milliamps of current. That's a little on the hot side for an LM358, so let's try driving the current with something else. We can use an NPN transistor instead. The 2N2222 can drive over 500 milliamps of current. The trick is to put the transistor's base and emitter into the feedback loop. We'll put the LED back in the circuit by connecting it as the transistor's load. All that's left is to connect the LED to the positive supply voltage. This new configuration will work because the current flowing through the collector and the emitter is virtually the same. We should stop and check electrical rules again. Our final test circuit won't include the actual LED. Instead, we need a 2-hole connector socket to plug in the LED. We'll also need a 2-pin connector for the power input. Let's take another pass at cleaning up the design and run one last rules check. Join me next time to prototype this circuit on a breadboard. This has been Not Your Dad's Math. Thanks for watching.